Hi, thanks for watching our presentation. I'm Q, working for ASAPP Speech, and I today will co-present with my colleague Josh.
Hi, I'm Josh. I work for ASAPP NLP.
We are presenting our work ASAPP ASR, Multistream CNN, and Self-attentive SRU for state-of-the-art speech recognition. This is our outline of the presentation. We first present the overview of our system, followed by the detailed description of acoustic model. And we present the details of the language model architecture. After that, we show our experimental setups for both AM and LM and analyze our system's performance on the LibreSpeech dataset. Let me start with the overview of our works. In this paper, we built a hybrid ASR combining two novel architectures, Multistream CNN for acoustic modeling and the Self-attentive SRU for language modeling. We combined these two components by shallow fusion and achieved the state-of-the-art result on the LibreSpeech dataset. 1.75% word error rate on test clean and 4.46% word error rate on test other. To our best knowledge, 1.75% word error rate is the best published result on test clean so far without any extra data being used for either AM or LM training. Multistream CNN. For robust acoustic modeling, we leverage the benefits of Multistream CNN. This novel neural network architecture accommodates diverse temporal resolutions in multi-streams to achieve robustness. As the figure shows, the architecture is composed of a few streams of 1D convolution and with the different temporal resolutions, following a few 2D convolution layers in the earlier stage. The 1D convolution layers, here we use TDN and F layers specifically, have their unique dilation rate, resulting in diverse temporal resolutions across multiple streams. Each stream stacks 1D convolutional layers up to 17 layers. At the end, the output embeddings in the streams are concatenated and go through ReLU, batch-norm, and dropout. Let me stop here and hand the presentation over to Josh for more details on our language modeling.
Thanks, Q. We will now discuss our novel language model architecture, the Self-attentive SRU. The simple recurrent unit, or SRU, is a light recurrent network that balances model capacity and scalability. It's been shown to achieve significant speedups compared to the LSTMs on classification, question answering, and language modeling datasets, while delivering stronger results. A single layer of SRU involves the computations seen on the left. W, WF, and WR are parameter matrices, and VF, VR, BF, and BV are parameter vectors. This architecture can be decomposed into two subcomponents, a light recurrence, the first two equations, and a highway network, the second two equations. Because the light recurrence component uses a pointwise multiplication of VF and CT-1, the dimension of the state vectors become independent and therefore parallelizable. To enhance parallelism, the matrix multiplication is batched across all time steps as shown in the computation of U. Next, computing the remaining pointwise operations are compiled into a single fused CUDA kernel. The diagram on the right shows these two components. Our variation to the SRU is a simple one. We simply replace the matrix multiplication to compute U with the typical multi-head attention mechanism. This increases model capacity while providing faster speed compared to a transformer architecture. I'll now hand it over to Q to talk about experiments and results.
Cool. Let's see how we set things up for our experiments. The acoustic model training was bootstrapped with Caldi's standard LibreSpeech recipe. The models were trained on the LibreSpeech dataset of 960 hours. Regarding the model architecture, we employed 3 streams of stacked 1D convolutional layers in Multistream CNN. These 1D convolutional layers, as I said in the previous slide, TD&F with the different dilation rates. We applied 3, 6, and 12 as a dilation rate in each stream. The kernel size of each convolution was 3 by 1 with the embedding dimension of 512. Each stream of TD&Fs has 17 layers following 5 layers of 2D CNNs. We used the exponential decay in training scheduling with the learning rate starting from 1 to the minus 3, decreasing 1 to the minus 5 with the mini batch size of 64 through the entire epochs of 6. We took the advantage of 8 NVIDIA V100 GPUs for our training. We used the SpecArc for data augmentation during training too.
We construct our dataset for language modeling by combining the normalized text corpus of 800 million words with the transcripts from the 960 hours of training data, resulting in a final dataset of about 810 million words. When training our neural network models, we train at the utterance level. That is, the models do not leverage any context past sentence boundaries. Using our combined dataset, we train a custom character-level BPE tokenizer with a vocab size of 10,000. During training, we limit the maximum sequence length to 275 tokens, which truncates less than 1% of the dataset. During evaluation, we do not limit a maximum sequence length. We prepend all utterances with a special start of sentence token and append with a special end of sentence token. We train a 12-layer and 24-layer self-attentive SRU with slight variations in architecture. Both models rely on a hidden size of 2048 and a projected dimension of 512. We use an R-atom optimizer with a cosine annealing learning rate scheduler. The initial learning rate is set to 2 to the -4th, and we distribute training across 8 GPUs for each model, using the largest batch size that fits into memory, given the model size and GPU type. For the 12-layer model, we use an embedding size of 2048 and tie the input and output weights. Additionally, we use a single-headed attention mechanism in our self-attentive SRU. This results in a 77 million parameter model that we train for 10 epochs. For the 24-layer model, we do not tie weights, use an embedding size of 512, and rely on two-headed attention. This model is 139 million parameters and is trained for 12 epochs. Finally, in order to properly compare self-attentive SRU with a transformer model, we train a 12-layer transformer of comparable size to the 12-layer self-attentive SRU, using the same tokenization scheme. We use a model dimension of 768, a feed-forward dimension of 2048, and 8 attention heads. Like with our 12-layer SRU, we tie input and output weights and use the R-atom optimizer. We use a cosine annealing learning rate scheduler, but add a linear warm-up as well. We train for the same number of steps, 10 epochs, and this results in a 74 million parameter model compared to the 77 million parameter self-attentive SRU. The table in the top right shows the perplexities obtained on the dev sets for our 2 self-attentive SRU models and the comparable transformer model. With the 12 and 24 layer SRU language models, we achieved dev clean perplexities of 36.2 and 34.3 respectively. What's important to note, however, is that we see the most improvement in the first third of training with a combined dev set perplexity of 40 for the 12-layer model and 37 for the 24-layer model. When comparing our 12-layer SRU to the 12-layer transformer, we see that we achieve better perplexity using a comparable number of parameters. Notably, not only do we achieve better perplexity, but we converge much faster. To the bottom right, we show the dev perplexity curves of the 12-layer SRU and transformer models. The vertical lines showing each model reaches a perplexity of 40 on the overall dev set. The transformer requires 1.2 million steps to reach this perplexity, while the SRU model takes only 622,000 steps. This is almost a 2 times training speedup, which in practice reduced training time by almost 2 days.
Cool. This table shows the results of our system with different configurations. In contrast to the baseline TD&F acoustic model with a 4-gram language model, we can see that the multi-stream CNN with the same language model outperformed by around 13% relative improvement on test other. The N-best rescoring with the self-attentive SRU language model brought dramatic improvement to further improve the word error rate by around 23% relative, as opposed to rescoring using the TDNN LSTM language model. We further lowered down the word error rate by applying the expected word error rate minimization when we rescore. This gave us relative word error rate improvement of 2% to reach 1.75% on test clean. Comparing with other state-of-the-art systems, we sit at the lowest in word error rate on test clean while being in the pack on test other, which is clearly seen in the table shown in the slide here. Let's wrap. To conclude, we proposed a hybrid ASR system combining the two novel neural network architectures in Multistream CNN and Self-attentive SRU for acoustic modeling and language modeling, respectively. The Multistream CNN AM provides more robustness to challenging acoustics, and the Self-attentive SRU LM is shown to be faster and more powerful than Transformer. We ASAP will continue to bring novel ideas to take our current system accuracy to new heights going forward. Thanks for listening to our talk today. Any questions, please shoot us an email. Thank you.